The next type of series we like to look at, the geometric one. So this one, another very simple pattern, but instead of adding the same amount, we're now multiplying by the same amount. And so instead of calling it a common difference, we call it a common ratio, symbolised with R. So if I want to work out what R is, I could get the second term divided by the term before it, third term divided by the second term, and so on and so on. I could pick any term divided by the one before, we'd get the ratio. But again, this can create a recursive formula. If I make term n the subject, then that would be a recursive formula for a geometric series. Okay, well let's create the general term from that then. So the first term is A. The recursive formula says I'll multiply it by R. So term 2 is AR, then AR squared. Again, the pattern starts emerging. So our general term, AR to the power of n minus 1. Now this one, when we plot it, we'd end up with an exponential function. Makes sense. Again, look at the equation. The unknown, the n, is in the power. So yeah, we should end up with an exponential equation if we were to graph it. Right, let's do this one. Here's our pattern, 2, 8, 32. What's the ratio and what's the general term going to end up being? So our ratio, well, first term's 2, ratio 8 divided by 2 is 4, so I know that. General term, AR to the n minus 1, okay, that would be a general term, but this one we can do better, because 4 I could rewrite as 2 squared. So playing around with all that, I get a general term of 2 to the power of 2n minus 1. Remember, we want to make general terms as simple as possible for the substitution. That would be a simpler thing to substitute into. How about this one? The second term's 7 and the fourth term's 49. What would the general term be? I don't have two consecutive ones, but I know AR, the second term, would be 7, and I know AR cubed is 49. So again, I've got simultaneous equations. This one presents an interesting problem though, because R squared is 7, which means there's two possibilities for the common ratio, and unless they give me more information, I don't know whether that ratio is positive or negative. That therefore means when it comes to working out the general term, I'm going to have to come up with two possibilities. Now, if I substitute this plus or minus root 7 in, that means the first term, it might have been the square root of 7, but maybe it was the negative square root of 7. General term, well, I'll say it's root 7 times root 7 to the n minus 1. I'll get root 7 to the power of n, but that was if that first term was root 7 and the ratio was positive as well. The other way I could do it is say this, well, what if they were the negative ones? And then I would get negative root 7 to the power of n. There's a better way of writing that with patterns, because essentially what we're saying is the plus minus is going to alternate. So you remember how we put that factor out the front, that negative 1 to the power of n, which will then control the sign of the number. So if n's an even number, that'll become positive. If it's an odd number, it'll be negative. So that's probably the best way. But I can't do anything else. So really I'm saying, hey, there's two possibilities for this general term. And unless you give me more information, that's the best I can do. How about this pattern? 1, 4, 16. What's the first one that's going to be bigger than 500? Right, first term's 1. We can see the ratio is 4. The general term then, wow, I don't need the 1 out the front. 1 times anything's 1. So it's just going to be 4 to the power of n minus 1 is greater than 500. We've got ourselves an exponential inequation to solve. Log both sides. That's how we can get that out of the power. Because the log laws allow me to bring the n minus 1 to the front, divide both sides by log 4, but remember, when you're dividing by logs, be careful. If it's the log of a number that's smaller than 1, you're actually dividing by a negative number. So you'd have to change the sign. In this case, it's fine. Log of 4 is a positive number. We want the first number that's bigger than 5.48, or the first integer. So 1024, the sixth term, is the first one that would be bigger than 500 in this pattern. I now want to talk a bit about these things called arithmetic and geometric means. Now this will become really important next year in Extension 2 when we're looking at inequalities and things like that. So I thought I'd just branch out a bit here. What are they? Arithmetic mean, you already know what that is. It's actually what we call average in statistics. It's the same sort of idea. It's when you add up every number in the pattern and then divide it by the number of terms in the pattern. And that's why sometimes when we're talking about averages, we call it the mean, because it's actually the arithmetic mean. There's also this thing called a geometric mean, where instead of adding all the numbers together, we multiply them, and instead of dividing by n, we find the nth root. That's what we call a geometric mean. Now the thing about a geometric mean, I can only find it if all the values are positive. You can't find the square root of a negative number, so you don't want that issue. And the geometric mean is also always a positive number. So unlike the arithmetic one, where you could get a negative arithmetic mean, you can't get a negative geometric mean. We're only dealing with positive numbers for this. Let's find the arithmetic mean and geometric mean of 4 and 25. Add the two numbers together, divide by 2, 29 on 2. Whereas if it was geometric mean, we'd multiply the numbers together, in this case 100, and find the square root of that. So it would be 10. What it allows us to do with these number patterns is it allows us to find numbers in between other numbers in the pattern. So if 2x, y and 128 form a geometric progression, x is in the middle of 2 and y. So x will be the geometric mean of 2 and y. So I know x would be the square root of 2y, whatever that happens to be. But y is in the middle of x and 128. So y must be the square root of 128 on x. Again, I've got simultaneous equations here. I should be able to now work out the numbers in this pattern. So y squared is 128x. Playing around with that, we get eventually, oh here we go, we've got this quartic that we're solving. So either y is equal to 0 or y is 32. Now I can discount the first possibility. You cannot have a geometric progression where one of the terms is 0. Well, I suppose you could, but it's a very, very boring pattern if you think about it, because every term would be 0. It's going to be y is 32. And now I can work out x. I've got the two numbers in there. So it's a different way of working out those numbers. I could have said, hey, the first term's 2, the fourth term's 128, work out the ratio. Could have done it that way. But it's another way of finding numbers in between other numbers inside a pattern. This is where we're going to have some fun. Okay. There are other means as well. There's all sorts of means. There's a thing called a harmonic mean. Oh, you're going to love this one. There you go. That's the harmonic mean, where you add up the reciprocal of every number and put that in the denominator, and instead of dividing it by n, you actually ends on the numerator. So it's sort of like the reciprocal of the reciprocals. We call this the harmonic mean. These three means have a relationship. So the arithmetic mean, the geometric mean and the harmonic mean are the three Pythagorean means. Then we have this thing called a quadratic mean. And the quadratic mean is this. We add up all the terms squared and divide that by n, but then find the square root of it. And that's a quadratic mean. And there's this really neat relationship between these four means. The quadratic mean will always be bigger than the arithmetic mean, will always be bigger than the geometric mean, will always be equal to the harmonic mean. You'll notice I said equal to as well. Again, equal to is really boring. That's just going to happen when simply all the numbers are the same. Because if all the numbers are the same, then the arithmetic mean is that number, the geometric mean is that number, the harmonic mean is that number, and so on and so on. So it's a bit boring pattern. But otherwise, you get that relationship. So let's now prove this little relationship here. A plus B is greater than or equal to 2 root AB. Now this will become a very important inequality when we get to extension 2 inequalities. But let's do it. How do you prove something? Remember, you're proving it. We don't know it to be true, we want to prove it's true. One way of approaching inequalities, start with something you know to be true. I know that's true, because if I square something, it's always going to be greater than or equal to 0. So a minus b squared will always be greater than or equal to 0. Therefore, I can expand that out, and now I can move that 2ab to the other side. Because I now know that's a fact, I can move things around. So I started with something I know to be true, I can then manipulate that round and get the result that I want. And there it is. Well, sort of. It's not quite right, is it? And that brings us to another idea. Once we've got a known inequality, I can substitute numbers in, because this is always going to be true for any number. So I do something, and the first time you see this done, people feel a bit uncomfortable. But what I'm going to do is I'm going to let a equal the square root of a and b equal the square root of b. They're positive numbers. I can substitute any positive number in there that I like. So I now know the square root of a squared plus the square root of b squared is greater than or equal to 2 times the square root of a times the square root of b. And I get my result. There it is. Now, I could have done it all in one hit by saying, instead of starting with this known fact of a minus b squared is greater than or equal to 0, I could have started with the known fact that the square root of a minus the square root of b all squared is greater than or equal to 0, and it would have done the two things in the one step. It doesn't really matter how you approach it. But these are a couple of ideas that when we look at inequalities next year, we'll see these ideas used quite often. What we have effectively done there is just proved that the arithmetic mean is greater than the geometric mean for two numbers. Because if I was to divide both sides by 2 now, look at what we've got. We've got a plus b over 2, the arithmetic mean, is greater than the square root of ab, the geometric mean. So we just proved that. The lovely thing in extension 2 inequalities is we are allowed to just quote that result, unless that is what you've been asked to prove. Obviously, if you've been asked to prove it, you can't say, oh, because arithmetic means geometric means, therefore it is. No, you've got to prove it. But if they don't ask us to prove it, we can just use it. Let's prove this then. The square root of AB is greater than or equal to 2 on 1 on A plus 1 on B. I now know this to be true. The arithmetic mean is greater than or equal to the geometric mean. So I explained that. I said, I'm making this bold claim, but this is why I can make that claim. The arithmetic mean is greater than or equal to the geometric mean. So I am starting with a known result. Now, I can't solve it like an inequation. I'm not solving this. I'm not trying to find the values of A and B. But I can use manipulation now because I know it to be true. Therefore, I can manipulate it and try and make it look like what I'm trying to prove. And so that's now the question I ask myself. How can I turn what I've got into what I want? I can do that. I know I want the square root of AB. How would I turn that into the square root of AB? Well, I'll multiply a plus b on 2 times 2 root ab on a plus b. That left-hand side would become the square root of ab. What happens on the other side? I've now got 2ab on a plus b. Not what I want. But once the left-hand side is what I want, it must be possible to turn the right-hand side into what I want as well. It's got to be possible, if in fact this is a true statement. So how can I turn this into this? So again, I'm looking at what I want. Top of the fraction, I just want 2. I've got 2ab. Oh well, I'll just divide by ab. What I do to the top of the fraction, I've got to do to the bottom of the fraction. But look what happens. I've got a plus b on ab, which is indeed 1 on b plus 1 on a, and that's what I want. So therefore I've got it. Notice the setting out. And this is why we work down the page in a proof. We don't go equals across the page. We go down because you're actually reading it. You're saying square root of AB is greater than or equal to this expression here, but this expression is equal to this expression, which is equal to this expression. Well, therefore, my first one must be greater than or equal to my last line. Okay? So that's why we work down the page, and the notation is very important. But what we've just done now for two numbers is prove that the geometric mean is greater than or equal to the harmonic mean. Let's do this one then. The square root of a squared plus b squared on 2 is greater than or equal to a plus b on 2. I'm going to start with something I know. A squared plus b squared is greater than or equal to 2ab. That is the arithmetic mean greater than or equal to the geometric mean. In 3 terms, it would be 3 times the cube root of the things multiplied together and so on. Well, that's what I've got. How do I get what I want? This one, a little bit different one, this one. I say, well, okay, I'm going to add a squared plus b squared to both sides. Now, it might not be immediately obvious why I'm doing that, but now I'm also going to divide both sides by 4. So on the left hand side I get a squared plus b squared on 2, but on the right hand side, hey, this is a perfect square, a plus b squared on 4. Very close to what I want. So a plus b squared on 4 is the same as a plus b on 2 squared. And I'll find the square root of both sides. Now I can do that because, and this is why I bring up this next important thing in your proofs, is it immediately obvious why I'm allowed to do this? So you always explain why you can make these non-obvious claims. I can do this because the y equals the square root of x is a continually increasing function. And when you're applying a function to an inequality, if it's a continually increasing function you're applying, the sign stays the same. If it's a continually decreasing function you're applying, then the sign flips. But what we've now done is prove that the quadratic mean is greater than or equal to the arithmetic mean for two numbers, thus completing that relationship between the four means. That was a lot more than we really need to know to do our exercise right now, but it was something interesting, something to look forward to next year.